Okay, we should make an effort to start a bit sharp because it's already 1 minute past 9. We've got a lot of lectures today. So welcome back to Vikraman's course on category theory for semantics. Vikraman.
Okay, all right. So, hi. Okay, so right. So okay. So before I start, I wanted to say some people said it was a bit dense. Some said it was too easy. We will. I think I might be jumping sometimes between different things. But I'm always happy to talk about things offline on outside or on Discord or Zulip, wherever. Yeah, and the other thing I want to say is I did not write any formal lecture notes, but I'll try to write some exercises, and I think it's because we are talking about abstract things. The way to think about it, you do the concrete proof once, and then you understand it, and then it becomes a part of you, and the next time you just use the proof, and so there's an abstraction ladder you have to climb, and you have to do it once, and that's why we do exercises, or we have problems to solve. And yeah, okay, so okay, and so just a quick recap of things. So we said there is an intuitionistic propositional logic with conjunction and implication, and then there are these things called Heiting semi-lattices, which have a top, they have meets, and they have an implication. These are the same symbols. When we just do semantics, we just turn one into the other, right? And this is justified by giving a translation like this. So if we know that phi derives psi, then I can produce a poset. And if I have a poset, I can show that it derives psi. A more formal way to say this is to just forget about the syntax and just say there is a free hiding semi-lattice on some set of propositions, or set of atoms X. And if I have a Heiting algebra, if I have a hiding semi-lattice, I have to give you an assignment with a valuation function, which tells me what the values of each atom are. And this intuitionistic propositional logic has a semantics which is uniquely determined by this valuation function. So let's say V here. And it's going to do the right thing. It's going to send tops to the truth value to the top element, the conjunction to the meet, and the implication to the implication. Okay, and this is what gives it a universal property. And then because this is sound in hiding algebras, in hiding semi-lattices, we want to we want to prove that something is not possible. So it is not true that we can derive P Q for any atom Q. So if you wanted to give a proof of this, what we want to show is that there exists some hiding semi-lattice H, and there exists a valuation function sending PQ to H, such that in the semantics of this thing that I call phi, it's not going to be true. Okay, that's just the top and H. Okay, and I left it as. Does anyone? No, I think we talked about it, right? So 0, 1, 2 is an example, but we have to actually give truth values to these P and Q. So I mean, I worked it out, so I know what it is. But so you want to choose the top element as the top element, right? And this is going to be the smaller thing. So 1 meet 2 is 1, 0 meet 2 is going to be 0. So this is a symmetric operation, so defining it like this is fine. And if I want to define the implication, I will say that this is 2. Okay, and 1, 2 is 2, 0, 2 is 2. But I also have to give the other way. So 1 arrow 0 is 0, 2 arrow 1 is 1, and 2 arrow 0 is 0. And when they're both the same, I will set this to okay. This so we have to still check that it satisfies the axioms of a semilattice. So for all p should be less than equal to 2. That's fine. And for p, q, r, r is less than equal to p meet q if and only if r is less than equal to p and r less than equal to q. And the axiom for implication, r meet p less than equal to q if and only if r less than equal to p meet q. Okay, so to check this, we have to go and check. Trust me, it works. And I still have to give you a valuation. So the valuation of p, I will give the middle thing, 1, and the valuation of q, I choose the lowest thing, that's 0. And then you can check that the meaning of this phi formula becomes 1, and 1 is not equal to 2. Okay, so this is a concrete counterexample. It's fine, but it looks like magic, right? So the only intuition you have is that there used to be 2 truth values for Boolean logic, but now I have 3, and there's a clever way of assigning valuations to these implication operations such that we can find counterexamples for classical formulas. Okay, and now, so these are numbers. We don't want to talk about numbers. We want to talk about algebraic things. And so numbers hide what is going on, and what we want to talk about is posets. Okay. So I think so power sets, where someone suggested power sets, right? So power sets, if I take power sets on 0 and 1, it gives you a very nice poset. So it's empty set, it's 0, it's 1. Okay, so this is a nice poset. We learned this in undergraduate power sets. So they have so the subsets, and they're closed under. This is the top. This is the bottom element. It has a top element, and it has unions and intersections. But power sets also have this duality. It's a complement. So the complement of this is the bottom. The complement of this is this. So there is a perfect symmetry in power sets, and that's what allowed us to define the implication operation as this thing. Sorry, union, right? But the fact that this decomposes like this and the existence of this complement is what justifies, the classical principles. So we can show that by going to Boolean algebras and classical logic, but let's not think about that too much. So the only thing I want to point out is that there is this complement operation which is kind of breaking this. We go from empty to 0 and we climb up. There are two ways of climbing up. But if you take a complement operation, you kind of switch sides. So, so there is a nice sense in which these paths are closed. Okay. So what if I could just get rid of this one element? I would get a 3-element poset out of the power set. So, so I chose these numbers 0 and 1 suggestively. So what I'm going to write is 0 less than equal to 1. It's the poset with on this 0, 1 set, which or let's just write this. So it's kind of the simplest posets that you can think of. So the simplest non-trivial poset. So 0 is less than 0, 1 is less than 1, and the only non-trivial arrow is the one going up. And one nice way of saying it is the simplest such thing. It's called a walking poset, which is a terminology. If you read the NLab or you listen to John Baez and James Dolan, they have this. So every time you define a structure, you should think about what is the walking structure. Okay, so what is the minimal structure you need to add to a set to get that thing. Okay. This can be made much more formal, but we don't have to think about that. So I give you a poset like this, and then I talk about. Okay, let's keep this, and I will talk about the downset of a element in the poset. So the downset of 0 is going to be the subset of elements in the poset which are less than equal to 0. Okay, so the downset of 0 is 0. The downset of 1, 0 is less than 1, 1 is less than 1, so it has 2 elements. Okay. So if you give me a poset, I can construct a collection of downsets like these, and then I order them with the less than equal to relation. So the downset of a poset is a collection of subsets. So I'm taking the power set, but I'm cutting down on the number of power sets, and I'm going to use the less than equal to relation in some way. So I'm going to say that it's closed under taking down, less than relations. So if Q is in S, right, and for all P in big P such that P is less than equal to Q, then P should be in S. Okay. So the downset of this poset is exactly. So let's take a look at the thing. So it's exactly this. Okay. So every collection of downsets, it's always going to have the empty set because the empty set has nothing in it. So it's always downwards closed. For every element in the poset, there's going to be a downset of these things. Okay. And now, so let's think about downsets. So given a poset like this, I will send it to a downset like this, ordered by the subset relation. And if I have a little p in this poset, I'm going to send it to the downset of elements smaller than p. Okay, and you can easily check that this. Chris told us about posets being categories. So as a category, these are the arrows, right? So if I know that p is less than equal to q, then downset of p should be subset of downset of q. This could be easily checked. Yes. So downset of p is the set of all subsets of p, such that for all q p in p, R in P, such that R is less than equal to P. And this has to be R in P, such that R is less than equal to Q. Okay. Everything here should be here by transitivity because P is less than equal to Q. Okay. So this downset operation does something really nice. It takes a poset and gives me a new poset. Let me call this the baby Yoneda. Okay. So a map like this, which I take a poset and I get a downset of posets, a downset poset. So why do I want downset posets? Well, here's one way. So I took a poset with 2 truth values and I produced 3 truth values. Okay. So downsets are very nice. So downset of P for all posets P, this thing is going to be a model of intuitionistic propositional logic. So it will be a the thing we've been calling is a Heiting semilattice. Okay, it's easy to check. So you want to check it has meets. It has a top element. So what should be the top element in downset of P? Should be the whole thing. Yes, P. Thank you. And if I have 2 such downsets, the meet should be the usual thing, intersection. Okay, it's yes, but there's something to check here, right? So you have to check that if S and T are downwards closed, S intersection T is also. Okay, so we should check it, right? So let's check. So if we know that we know that S and T are subsets of P. Yep. And for all, I'll just compact in. This is a compact way of writing that whole condition. Just okay, and for all less than Q in T. Okay, and we want to show that for all P less than Q in S intersection T, P is in S intersection T. Okay, to show P is in S intersection T, we need to show it's in both S and T. Because Q is in S and T, Q is in S, apply this, P is in S, Q is in T, apply this. Yeah, so break it down. Yeah.
You said there's something we have to check. The fact that we have to check this is because we're checking that the downward slope that is in fact Heiting semilattice.
Yes, and to do that, we need to check the axioms for each operation. The operation we defined was intersection. The side condition is this. Okay. Yeah. And now, so how do we define the implication? Okay, this requires some. So obviously this is fine, but it's really just too concrete. We don't want to work like this. If you keep doing it like this, then there will be always too much to check. Yeah.
Basically, what you're doing is I think semilattice is a sound and complete model for the intuitionistic
Yes.
that you're seeing.
Yeah.
You are giving a particular concrete example. You earlier gave an example with like numbers. You don't want.
Yeah.
And now
Yeah.
you are giving a different example.
I'm giving a general recipe for constructing such models.
Okay. So
Yes.
one more thing.
Yeah.
So in your version of IPL,
Yeah.
so how do you represent the knot?
So there is no knot. If I had a bottom element, if I had a hiding algebra, then I would just say A implies bottom. That would be.
So here you're saying that.
Yes. So there is an empty set. Yeah, I will. I'm saying it is a hiding semilattice, but it has something more as well.
But just from
Yeah.
Let's think you can derive that, right? I mean, so like you're saying that like some formula is not derivable.
Yes.
In there.
Yes.
So I can think of a knot of it. I mean, so let's say something is not derivable. A knot of it
Right. Yeah. So this is a strong completeness property which Boolean algebras have. If phi is not derivable in the Boolean algebra, then not phi will be derivable. These logics don't have this property, and yeah, we can actually prove that, but we have to get to stone duality and stuff. Yeah, I'm happy to talk about it more like after. But yes. Right. So we want to define the implication, for which. So these downsets are fine, but this is a very concrete definition with too many side conditions. So we will fix. We will like build some tools to work with downsets. So the first thing I will say is if S is such a downset, then you can think of this S as being generated by this down arrow thing. So S will be equal to all the Q's in S union. So you take, so S is a subset of P, right? It has a bunch of elements, Q. You take those elements, you compute their downward closure, and then you union them, and you'll get back S. And this is a characterization of what S is. So every such downset satisfies this. So exercise actually check this. So for every S in S, you would pick S, the downset of S, to go on the other side. And if you have an element of this, it's in a union. So you check everything and come back to S. Okay. And the way to define the exponential, I will just we can work. Sometimes we just have to work backwards for things, right? So okay, this was so it is a meet. It has to satisfy the R subset of S intersection T, if and only if R subset of S and R subset of T. But this is kind of a basic exercise in sets and intersections. Okay. For implication, we are not using complements anymore. So for implication, so we have to define an operation such that R. So let's just replace the meets with intersection. Subset of T. If and only if. No, let's write it like this. So R S arrow T. If and only if R S. Okay, so this is, we want an operation, double arrow. Did I use a double arrow? Okay, let's use double arrow for the implication just to avoid confusion. So, right, so to do this, so we want for all R in R, R should be in this arrow T. And here we want here I will decompose this R using this characterization. So for all R in R, downset R, intersection S, is T. Okay, and this means that some bracketing should intersection S, if and only if intersection S instead of T, and now you've got it almost. So for all R is in S. So for all R, so I take the union. Yeah. So from these two steps, I can just define this to be this R such that okay, so I will take this as the definition of the implication. If R is still free. Okay, let me check my formula. Okay, so to define a set like this, which is downwards closed, and okay, so I take all the elements in P such that their downsets intersected with S is a subset of T, and this gives you the set of implications from S to T. Okay.
This one, pronounce that equational proof as located in someone who's got half a brother.
Okay, so the axiom for implication says for any two elements of my algebra, I would have to find an operation called implication, such that for any R in the algebra, R less than equal to S implication T, if and only if R and S less than equal to T. Okay, so this is the axiom we have to define a element which is which satisfies this. Okay, yeah.
The last one is actually the square one, and then immediately move into the bracket one, right? But that last one is meant to be the meat of the algebraic representation that immediately gets unfolded to intersection, or?
Yeah. The meat is, because I defined the meat to be intersection, so I'm writing the meat as intersection and the less than equal to as subset. Okay, so I break down the R as a union of a bunch of things. Okay, I can expand the bracket because taking families of intersections, it's a downward closed set. This, okay. And if I unpack the other definition, I want subsets. So for all R in R, I want R in S arrow T. Okay, and now I want a set S arrow T which makes these two things equal, and I choose this set. Okay, and that gives me an implication operation. Okay. So downsets have all this structure, and so I can pick any poset P, and I'll get a downset. Let's actually okay. Let's actually write down some downsets, which might make this much easier. Right. So I'll write P and downset of P. Okay. So if P is the empty poset, yes.
Sorry, I don't want to drag us back to that, but given the derivation, the step-by-step system, how did you then extract the definition for integration?
Yeah. So you want the smallest set of, sorry, not the smallest, but you want all the elements which make downset R intersection S less than equal to T. So you just turn this into subset notation. That's kind of the trick. Yeah. There's also, if you know that it's a complete Heyting algebra, you can always so what you want to say is that if you have all joins, you can just say it's the join of all the R's such that R and P less than equal to Q. This is how. So you take the set of all these things and do a join. I just moved the thing inside using the downset operation. Okay, yeah. So if I take the empty poset, let's say no, I should write empty. it should only have how many downsets? No, so it's all the subsets, but only those which are downwards closed. Yeah. So there's only one subset. So so it's on the singleton set, but it's not a subset of anything else. So it's the singleton poset, okay. And then if I take the trivial terminal poset, I should get so the terminal poset has but this is downwards closed. This is downwards closed. So I actually just get this figure, right? What if I do it to this? I get 0, 1, 2. Okay, and well, it's fun to keep doing this and notice how the number of elements changes. Okay, but you do this and you observe a interesting pattern. So this walking poset plays a very important role. If I take any poset, let's say, let's say I take this poset and I look at functions from this poset to the other poset. Okay, so well, maybe I should write booleans. So for so let's do this exercise first on discrete things. So power set of x for any set, I can turn it into a function from x to booleans. If you've ever done functional programming, so if I give you a subset of x, I will generate a function called the characteristic function from x to the booleans. Okay, so if you give me an x, I will output 0 if, or let's say I'll output 1 if x is in S, 0 otherwise. Okay, and given any function like this, I can output a subset which is all the elements of x such that f of x equals 1. Okay, so this Boolean object is maps into the Booleans, gives me all the power sets, right? So this Boolean object has a special status in sets. It classifies things which are power sets. Okay, a similar thing happens with the 0, 1 object. So 2 equals 0 less than 1. It's a poset. So just so if I take the poset 0, 1 to 0, 1, there are, so it's a 2-element set. There are 4 functions. So 0 to 0, 1. I can write 1 to 0, 1, 1 to 0, 0 to 1, 1 to 1. Okay, so the truth table of 2 times 2, 4 functions. But now it's a poset, and I ask for maps in posets, so they have to be monotone, right? So this function is monotone because 0 goes to 0, 1 goes to 1, right? Here. 0 goes to 0, 1 goes to 0, still monotone. 0 goes to 1, 1 goes to 0. So that's crossing the monotonicity relation. So we're going to rule this out. And 0 goes to 1, 1 goes to 1. So that's valid. So you have only 3 monotone functions from the 0, 1 poset to the 0, 1 poset. Yeah, unlike power sets where you have 4 functions. Okay, so you do this and you realize, oh, okay, so there are 3 things here, 3 things here, and you keep doing this. And so a good intuition to keep in mind is that so I have booleans. So these booleans also. So what are the maps in POSET from x to 2, or sorry, p to 2? Okay, and does it connect to downsets on p? Okay. So given a downset S, so a downward closed subset of P, I can produce a monotone function. Can I produce a monotone function? So P to 0 less than equal to 1. So given a P, I do the same thing. 1 if x is in S and 0 otherwise. Okay. And if you do this exercise, you'll see that you have to just turn around the direction of the arrows at some point. So downsets from so downsets on a POSET P and monotone functions from P up to 2. There is a bijection between these 2 sets. So if you give me a function, a monotone function here, I can produce a downset, which is again the same formula for x in P, such that f of x equals 1. Okay. So we have like a few different. So let me write things down a bit more. So these are some tools, or you analyze the structure of downsets and you arrive at these conclusions. So one, or any S in downset of P, S is equal to P downset of R. Okay. Downsets of P is something like this. Okay. Number 3, downsets of P are in bijection with POSET maps from P up to 2. Okay.
That's probably number 1.
Oh, sorry. Yes. Yes, that's right. Yeah, and finally, so there is a map of POSETs from POSETs to downsets and POSETs given by this thing. Okay, and okay, and I should also say that actually downsets are so now that we know this fact, we can actually so there are different ways of computing in downsets, right? Okay, so I'll say one more thing, which is if P itself is a Heyting semilattice, then this map preserves meets and implication. So this is also we should check this. But this is very easy to check once you know the characterization. So for something to preserve means I'm constructing a homomorphism of Heyting semilattices. So this map, so first it should preserve the greatest element should be equal to the top element in downset P. So this should be obvious. The top element in downset of P is P itself, right? And so what is so it's given on object by the downsets. So and P is equal to the downset on P. Right. So everything in P. Okay. Check. So why does okay? So want to show this is this, and this is P itself. So this is the set downset true, which is the set of all P such that P is less than or equal to true, but everything is less than true, so it's P. So P is equal to P. Okay. Second, it preserves meat. So if so for all P and Q, if I take the meat of P and Q in P, I apply Yoneda to it, and I want to show that this is, or it's the equational reasoning style. Okay, and this is the downset of P intersection Q, which is the set of all R such that R is less than or equal to P meet Q. But the axiom for P meet Q exactly says that this is equal to the set of R such that R is less than or equal to P and R is less than or equal to Q. And this is an intersection. So and this is exactly downset of P intersection downset of Q, which is by definition Yoneda P meet Yoneda Q. Okay, a very simple proof, but all it's showing that this map actually preserves the meat, and it's just applying a homomorphism thing. And the final thing you want to check is implication, but now that we've built some properties of this map, it's easy to check this thing. So we want to show that this thing is Q. Again, we'll do a backwards kind of reasoning. So, so what we want to say is that this is exactly the exponential in downsets, right? So I'm sending exponentials to exponentials, and this is going to be an exponential if for all R in downsets of P, R meet Yoneda P. Sorry, R is less than or equal to P. Arrow Yoneda Q. If and only if R meet Yoneda P less than or equal to Yoneda Q. So this is what we have to check. So it's the same proof, but now written using the Yoneda. Same proof as earlier, but so so if it's an R, it's fine. So I will also R. So P has exponentials, right? So okay, I think I'm stuck. Not sure what's going on. So R should be okay. Okay, so we have to now actually use the formula for this exponential, but I thought there might be a trick. okay, I think I'll just leave this as an exercise. You should be able to use the fact that it preserves meets to actually move the thing inside, but we can talk about it later. It's fine. Right. Functions. Right. So, yeah.
I want to ask whether we could do a little like recap because we started to have intuitionistic topic and like textbooks you will find Python algebra when
Yes.
there's a semantics and you introduce the semanticists.
Yeah.
So and now you introduce like the concept from the process to the sound
Yeah.
thing, and you wanted to do categories with semantics, and since we started this, I have to think of something like PC.
Yes. Yes.
And
Yep.
for my question, we could do that as a broad interlude with the complete picture.
Okay. Yeah. So I was trying to get to yes. Oh, repeat. Okay. So the question is, we've been doing logic and functions from functions between posets and monotone maps, and what is the picture of what we're going to do? So yeah. So I'm talking about logic and posets, but the next step would be going from logic to type theory, and from posets to categories, where all of these structure, this structure exists, but you have to do it in posets to actually believe in some of these things, right? And then you categorify and you imagine, oh, everything should just, happen the same way, but instead of less than equal to, we'll actually have, sets of arrows between things. And when we go from intuitionistic logic to, so textbooks do talk about hiding algebra, so maybe so that's the second thing. So downset of P is actually a so it's a hiding algebra. So I've been saying hiding semilattice, but if the semilattice is a real lattice, it gets called a hiding algebra. So a hiding algebra has a top and a bottom, and a meet and a join and an implication. So the thing we skipped over is the false and the meet and the join, right? But these downsets actually do have the structure of a hiding algebra. So the empty set in so the bottom in downset of P is the empty set, and S join T will be the union of the two subsets, okay? And the hiding algebra, so it's a okay. So when we start speaking the language of categories, all this becomes very simple. But now I'm trying to remember. I think it is a lattice, which is so it will be distributive because of having an implication, but it's a lattice plus implication. So a lattice has the structures. So it has a top, it has a bottom and a top, and there's stuff in between, which is less than equal to. So hiding algebra. So if you go to full intuitionistic logic, which has conjunction, disjunction, and implication, hiding algebras are the model. And in fact, and then you notice that this implication operation, exactly that this plays the role of negation, right? So you can define a negation operator in hiding algebras, but it's not like complement, because negation A does not imply A from the hiding algebra axioms, okay? And that's why they're good models of intuitionistic logic. Okay, so that's the big picture. These lemmas about okay. So, and also, why did I not talking about hiding algebras from the beginning? Well, this fact that I said here about it preserving meets an implication, it doesn't preserve joins and the bottom element. So that's where things break. And I'll try to just avoid talking about sums unless there's time. So then the point is to go from this fragment of intuitionistic logic to simply type lambda calculus, and Right, and the okay, and before I end, I mean, for this thing ends, I should say finally the what is the point of all this? I mean, we've seen Kripke semantics in other talks, right? And actually, what I just showed you is Kripke semantics. So let's see why. So what I want to say is I have the free heighting semilattice on X, and this is my my evaluation function, which assigns atoms to downsets, gives me a semantics for this. So just think of the semantics map. It goes from f of x to downsets of p. And we just saw downsets of p are isomorphic to poset p op, comma 2. And the category of posets is Cartesian closed. We will see more about Cartesian closure later on. So, so it just means that you can think of these as exponential objects. So when you have exponential objects on the right, you can curry them. So f of x times p op arrow 2. Okay, so giving a semantics of what is it? The intrinsic proposition logic or the free heighting algebra in downsets is equivalent to giving a forcing relation between formulas in the free heighting algebra and a poset. Okay, so what is Kripke semantics? It says exactly this. We have a poset P, and which is supposed to be the set of words, right? And I have to give you a forcing relation and say that in some W in P, W phi. So okay, it's just the other. Okay, sorry. Next. So W forces a formula in phi, and that's when it sends it to 1. So that's the condition. So if you work backwards, you will rediscover Kripke semantics. And the fact that this is a homomorphism, it's a homomorphism of heighting algebras, just translate it back to this forcing relation. So the forcing conditions of Kripke would be for every W, W should force the top element. And okay, so the fact that also it has to be monotone, so the monotonicity condition has to be for all v less than equal to W. If W forces phi, then P forces phi. I hope I did not mix up my ops, so we should be so this is a Kripke model. And for all W, if W forces phi and W forces psi, then W must force phi and psi. And third thing, and for all W forces phi and psi. Oh, sorry. These things should really, if and only if. Okay. Don't use this as a definition. It should be in a proper textbook. But if and only if for all V less than equal to W, if V, if W forces then W should force. Okay, so these Kripke forcing conditions plus the monotonicity condition and this forcing relation, you curry it, you get exactly the free extension of the valuation. So okay. Right. So Kripke models are things that are used in logic to prove counterexamples and to show that some axioms are independent from adding to your logic. This is a completely algebraic way of looking at Kripke semantics, and it's important to programming languages because we can easily go from this presentation of semantics to semantics of programming languages by switching out from posets to categories of presheaves and going from the free Heiting algebra to free Cartesian closed categories. And that will be the content of the next lecture. Okay. And 3 minutes, so I'll stop.
Thank you, Vikraman. Any questions?
Yeah. Okay. I just looked up your definition of F from last time to get a better intuition of how to interpret it or how to use it for like giving semantics to a construction I want to give semantics to. And F was like the left adjoint to the forgetful functor from the category of Heiting algebras to the category of sets.
Yes.
And you say it's a free construction, therefore, and so could I interpret it as like f of x is something like the term algebra of my formula signature, so it's my syntax, and I give it
the term algebra is exactly the rules of logic. Mm-hmm. So you turn those into equations, and you get exactly the axioms of Heiting algebra. So the free thing is the one.
Yeah. So the construction you now made is simply, okay, give me the syntax of your formulas. This is how you construct a valid semantics for intuitionistic. Okay, thank you.
Like I've seen a version of intuitionistic propositional logic with Heiting algebras as a sound and complete model. So the IPL you have presented here, are they the same or like?
No, it is really a fragment.
Okay, yeah.
So they are. So I did not talk about the completeness theorem, but it essentially follows by just playing around with this initiality and.
Okay, so
they are complete for Kripke models, and it follows from just the fact that it preserves meets an implication. So you take P to be your f of x, and then you force it in its own model, and that gives you completeness, Kripke completeness.
Okay.
So this trick works for if you only have meets and implication. It won't work if you have coproducts, and that requires other tricks. Yeah.
All right. All right. So that's why you have a presentation in this way.
So these are strongly they're complete for like deduction, right? So if you prove something in these downsets, they have to be true in the logic. Yes. And when you go to programming languages, now it's not just about provability; it's about equations. So if you prove two programs are equal in the model, are they equal in the syntax? Well, for that you need something more.
Yeah. Okay. Thank you.
Yep.